when we create a scientific model, we have to be very careful, because what we may be falling prey to is a minor version of this projection issue that we have been speaking about, because we tend to make the model using elements that we already know, and by definition that tends to obfuscate at least a certain portion of what we are actually trying to figure out. When somebody is speaking to you in a totally different language and some word sounds like a word from your language, that does not automatically mean that that's what that word means, the same thing in your language, right? You have to wait to figure out the rest of the language and see if it is coherent with the whole thing. And then you can come across and say, okay, I think this is what that person is saying. Nature is the same way. Nature requires us to have patience to figure out the coherence of all the phenomena that you're seeing, rather than saying, that went that way, and so it kind of bounced like a tennis ball, so let's assume it's a tiny tennis ball.
Welcome back to Demystify Science. Today we have a conversation about the nature of science, technology, and the relationship between them, from which a certain type of natural ethics emerges. And our guest, Dr. Gopi Vijaya, is a scholar originally actually of solar physics who has gotten more interested in the moral valence of science and technology and the art of modeling. And so his proposition is that perhaps by more fully understanding nature from the fundamentals, more fully understanding what is charge, what is electromagnetic radiation, what is gravity, we can actually look to see how nature works, and by seeing how nature works, produce technologies that are less wasteful and less artificial and more closely aligned with the natural world. And so thereby better?
Yeah, I guess he would come up with an even more radical perspective that models are not a good idea in general, that we rely on models too much. We start to believe in the sound of our own voices a little too much, something like that. And so it's very radical. And in there, I think, is a really good point about our reliance on our early assumptions and how those snowball and get out of control, to the point that we have entire electromagnetic worlds built without understanding what electricity really is. So all of our favorite topics, basically, this is an awesome wide-ranging conversation about demystify sci intrigues. And so I think you're going to enjoy it too.
And also there's an opportunity to continue looking deeper into it if you're interested, because Gopi is organizing a conference for the end of October in the Bay Area called Renewal of Science. And it's going to be this interactive couple days where scientists from all over the world are going to come bring demonstrations of their work. People will gather for talks and poster sessions and all of the other things that come with these sorts of scientific conferences. But it's a really boots on the ground way of getting more involved with this. So if you're in California or you're traveling to California, consider checking it out. We talk about where you can find it at the very end of the podcast.
Remember, guys, we have no sponsors. We have no ads plastered over this podcast, and we're only able to do that because our amazing patrons support us directly. So if you like what's going on here, please consider giving us the smallest amount of money every month, which will allow us to put more and more time and effort into this project and not have to bow down to classic methods of making money with programming, which we absolutely loathe. We just find them distasteful, that's all.
And you can provide us funds for buying wigs instead of needing to get sponsored by a wig company in order to be able to fulfill our vision of just progressively larger and larger hair.
There's a lot of comments about our hair in the comments on YouTube, so
mostly Shiloh.
We really want to work
he wears a wig.
we want to work towards actual Newtonian wigs. So if you could just support us on Patreon so we can afford huge wigs, we'll really appreciate it.
And thank you to everyone who has already donated to our wig funds. We really appreciate seeing you every single week. For everybody who wants to contribute, come over to patreon.com/demystifysci, and hopefully we will see you there. In the meantime, enjoy our conversation with Gopi Vijaya, and we will see you next time.
The scientific revolution starts now.
The Demystify Sci podcast. Let us see in the dark.
I wondered if we could start the conversation with a question,
Yeah.
Sure.
which is, what do you think is the difference between science and technology?
Yeah. So I think when we are looking at these two, for the most part, for the initial impression, they have been melded together. So the distinction doesn't automatically present itself. But once we start looking at the roots of it, I think science as such is a way of coming to terms with the world around us in terms of how things work, and we are able to form clear ideas about how things work, and those ideas are tested out experimentally. So basically, experiments are a dialogue that we have with the world. We pose a question, it responds something, and we talk again, and then it responds something. So we are dialoguing with the world, and in that dialogue, sometimes you understand, sometimes you think you understand, sometimes you say that nature doesn't understand, whatever, depending on the situation. So all of these processes take place, and kind of towards the later part of this, where we feel like we are actually understanding something, and then we start doing most of the speaking, and that, I think, is technology. So initially it is what we hear from the world, and when we kind of talk a little bit, and then we start talking and we start participating. So what is done in experiments takes on a full-fledged form, a permanent shape, and that is what we are like pouring into the world in terms of our creations. We have arranged this thing, we have arranged this instrument this way, we have arranged this set. So it's like a experiment made permanent. That is what a technological object is, an experiment made permanent. So it's frozen into different things. And in that process, because it starts with the dialogue with nature, and it starts with our dialogue with nature, it inherently is based on what we have to say. So our own structure shapes and configures what happens in technology far more. So it really bears our stamp. As humans, it bears our stamp way more. And then that also is a little bit of a difference between how we look at science and how we look at technology. Science, we are still dialoguing, we're understanding, we're thinking, we're interpreting, we are figuring stuff out. And in technology, we start pouring ourselves out. So that is how I would kind of differentiate the two streams. And it's a very critical question also, because there is a fundamental belief that because I made this the technological problem or a technological object, I'm kind of in love with my creation. So because of that love for my own creation, we want to view the world through that lens. And so we tend to see everything, including science, including social science, including social relations, including everything, a worldview. We start seeing that through the lens of this product that we have made. And that is what I think has led to the enhancement of what we value technology as being, and therefore it is eclipsing other categories of our world, even if we don't realize it. So,
Can you give? I think I follow you and I agree with you. Can you give a specific example of an instance in our world where that's happening?
yeah, so multiple. Like you have one classic example in psychology called projection, right? You kind of put out what you are thinking inside, And we did that throughout the scientific history. For instance, you had the Homo machina. So you had this late 19th century images of the internal of the human organism being depicted as a factory, as, you know, like a telephone exchange at the top in the brain, a lot of, chemical reactors in the stomach, and chemical factory almost, and then so on and so forth. So you have this entire human organism, but inside people have made drawings. They actually see, what uh, they think exists inside in this way. And what is that a symptom of? Well, guess what they're surrounded by? They're surrounded by factories. They're surrounded by telephone wires and poles and these kind of things, and telegraph. They're surrounded by these things, and that configures how they see things inside. And that,
Today, it's kind of like the mind as a computer. I feel like that's the most popular version
that's
of
our
this.
version of it. So now we are in the end of 20th to the 21st century. During the turn of that time now, we have latched on to our newest tech, which is what we are interacting over: the computer, the mobile phone, the internet, the radiation that makes all of it happen. And that becomes almost a subconscious mold for looking at things. And you see all of neurobiology like that. You may see the entire human organism like that. You might see the world like that, and yeah, because we are surrounded, for example, with everything that is heavily based in electricity. You will think the world is only made of electricity, things like that. So you have projections, unconscious projections that kick in, and we don't realize when we're doing it, but we're doing it all the time.
And the danger being that it might limit your solution set to some extent. Like if you think of the mind as a computer, you might be looking for computational solutions to
Right.
problems of the mind, let's say,
Yeah.
or on various just uncomfortable states
Yeah.
of being, let's say.
I wonder if you can explore a little bit the distinction between humans and nature, because I think that this is kind of an important aspect of the papering over of the natural world with technologies, which then stand in for explanations for the natural world. And I feel like I go back and forth between the idea of humans as natural and as very unnatural on almost a daily basis.
Right, of course. So just to complete out the thought that you mentioned, Charlotte, was, if it is to be expressed in a phrase, it would be the man with the hammer. Everything looks like a nail. So that's that theme which we are speaking of earlier. And to your question, Anastasia, it is the distinction between what is natural and what is not. So here, I think this ties into it, what we had just discussed, because when you do something technologically, many times in harmony with the laws of whatever you are shaping or forming or modifying, if it is in keeping with those laws, then it feels natural. For instance, I'll give you an example. You have all the different plumbing that's done across the cities everywhere, and if you notice the plumbing and everything, um, they are made with a mentality that tries to make sure the best material is used for the maximum extent of services, but very few people are looking at the shape of the pipes with a view towards the nature of water. That doesn't really come in. For instance, you have sharp bends, right? You have sharp bends all over the place in pipes and 90-degree angles and same uniform thickness and all of that. None of that takes place anywhere in the liquid world, whether you're dealing with blood vessels, whether you're dealing with rivers, whether you're dealing with anything in the natural world as such, where it exists without your participation. You don't have that. But some people have clued in to that difference. Like you might have heard of Victor Schauberger and some of his research, which several people are fascinated by. And that work is interesting because he was somebody who is uneducated in the usual sense of the word, but he was deeply educated in the forest of Austria. So he was a forester. He spent an enormous amount of time dealing with just the landscape of the forest and observing the water. And he said that, look, the way we are handling water is completely, you know, at odds with the nature of water. We are not cooperating with it. We are imposing things on it. We are basically forcing it into the mold that we choose. But if you go with the flow itself and understand how the flows actually work, then you end up creating entirely different shapes for the transport, the use, the handling of water, and so on. So he made several different designs, and each one of them have an artistic beauty to them because water itself creates very artistic forms. So here you are coming to the crux of it, I think, where it natural, the products that Schauberger ended up creating, or is it unnatural? So here you see that the natural as such is what already exists outside with minimum participation. It gets unnatural when we try to shape it in a way that it's not in keeping with its original form. And then it it more comes into the human world. Maybe this is a completely different meaning for the word supernatural, where we take it up in a way that is in harmony with the laws that it belongs to, and yet we are creating something new.
Hmm.
So now we have a different kind of thing in the world, which is neither just nature as it is given, nor is it violating the laws while we are making something, but it is actually going along with it as we are making something. So this is a little bit of how I process that difference
And it
that you were
seems like
looking at.
this difference creates a pretty robust framework for looking at technology in terms of what is effective and what is good versus what is destructive and what is extractive.
Correct. Exactly. So whenever we end up trying to squeeze um, a cylindrical block through a square hole, then you end up shaving off some of its ends and you do violence to that cylindrical object. And when we do that in our technological applications, we just call it an unwanted side effect. We never go back to the drawing board and say, hold on, maybe we're trying to put the wrong shape into the wrong slot. That doesn't occur. So instead, we say, oh, don't worry about it. 80% of it got through. No problem.
Mm-hmm.
Remaining 20% unwanted side effects. So you take that kind of mindset and you multiply it, exponentially, and there you have the destructive power that comes with technology because it's at the very foundation. You have the wrong. You're trying to fit the wrong thing into the wrong box.
I really appreciate this frame for looking at the world. The first thing that I wonder is, has there ever been a time where there was an era of technology that didn't work this way with a lot of collateral damage, or if this is just the inherent side effect of technological progress?
I think there were probably times when our shaping of the world around us was not entirely mechanical. We have a particular worldview which kind of came up more since the 15th or 16th century, which is predominantly mechanical. And in that sense, and now it is more electrical, I would say, that particular worldview, I do not think existed prior to that time. So even if they did mechanical things, the mechanical worldview as such is something different. I'll give an example, right? When you look at Aristotelian physics and you see the descriptions of something as simple as a flying arrow. And you look at the descriptions and you realize what he's talking about as to how an arrow flies in the air. uh, the description is almost exactly as if the arrow was alive and it was swimming like a fish through the air. The description is remarkable as to how like organically filled it is. It is a misfit for sure.
It
Because
is the will of the arrow to follow its path.
yes, it's like how you push the air back and how you push yourself forward continuously, and it is a very living description of an arrow or a ball. So they were amazing in terms of the devices that they brought out. The Greeks were one of the most, remarkable in that sense. We still look at the anti-Kythera mechanism and we are astonished at the mechanical, brilliance that went into creating that. And so we do the projection now in time. We say, you know what, they had excellent mechanics back then. Probably true, but not exactly in the way we look at it. We look at it very differently. Like post 15th, 16th century, we started actually understanding how a ball flies in the air, how an arrow goes in a parabola. Parabola, as such, was a word that was used for physics properly for the first time only since the time of Galileo. So, the mathematical genius of the Greeks was what created the conic sections. But the mechanical mindset of the late 15th, 16th, 17th century was what ended up utilizing it in order to understand the world in a mechanical sense. So there we are seeing different worldviews, even if outwardly the device and things like that could be similar. So I think
I feel like we also haven't reached the end of that story either. Like people will look backwards 1,000 years from now and perhaps point to a number of our explanations as if they sound just as absurd. We have large celestial bodies produce this attraction to one another we call gravity, right? And it's got a force, right, which sounds very Star Wars, and it right, and so you can see how this certainly has evolved since the time of the Greeks, but that there's plenty of evolution left to be done.
Yeah, exactly. And that even that very phrase, right, the force, it is a product of viewing the world as a mechanism, because as a mechanism you're dealing with forces. That's pretty much your entire world. And I would say it's almost a culmination of that worldview when we have in our sci-fi movie when somebody says, "May the force be with you." It's the culmination. It's almost deified. The force is deified
I
into
think so.
something higher. So you have that worldview. So when you're looking at technologies and to get back to your question, whether it is possible to do it, I think it is possible, and I think various other older civilizations probably had aspects of it which we find very hard to understand today because of what we have as our mentality today, and they probably had that at that time. But regardless, nevertheless, today we have to tackle problems the way we do it today. So um, as far as our work is concerned, we still have to figure out, okay, are we using the right approach for the right effect that we're looking at?
And in terms of, you say, in terms of our work today, can you lay out a little bit of the work that you do?
Yeah, so it kind of spreads in multiple directions. So since my background was more in material science and solar, and plonked me right in the middle of electromagnetism and thermodynamics and quantum mechanics and everything that you have to deal with, electricity and electromagnetism, all of it, all the different subjects. What I've been trying to do is to take up some fundamental questions that are at the root of several of these disciplines and ask good hard questions about it and explore that one by one. So one of the questions is about this idea of gravity. Where did that come from? Where exactly did it kick in mathematically in Newton's work and others as well? Or another topic that I've been investigating is color, and what does color mean in terms of how we understand it using physics, how we look at it using just what we see with our eyes, how do we make sense of all the different colors that arise? Do we really know all the colors that arise in the usual way? Can we measure them all the same way? All of that. So again, we're trying to identify the critical point where we speak about wavelength and color. So that will be the like one single point of attack, as so to speak. And so like that, different areas of physics have been trying to work on, and same with electromagnetism. And the guiding theme of the work is, can we try to understand this without imposing a model on it?
Hmm.
Can we
That's like
just
pretty antithetical to the whole practice of science, which is that we can only understand through models.
yeah, and that takes some sifting. And I think the reason is, when we create a scientific model, we have to be very careful, because what we may be falling prey to is a minor version of this projection issue that we have been speaking about, because we tend to make the model using elements that we already know, and by definition that tends to obfuscate at least a certain portion of what we are actually trying to figure out. It's like when somebody is speaking to you in a totally different language, and some word sounds like a word from your language, that does not automatically mean that that's what that word means, the same thing in your language, right? You have to wait to figure out the rest of the language and see if it is coherent with the whole thing. And then you can come across and say, okay, I think this is what that person is saying. Nature is the same way. Nature requires us to have patience to figure out the coherence of all the phenomena that you're seeing, rather than saying, that went that way and that way, and so it kind of bounced like a tennis ball. So let's assume it's a tiny tennis ball. Voila, you have a model. Now, every aspect of that process, which doesn't have anything to do with a tennis ball, gets obscured because you've now plonked a tennis ball on top of it. So
It usually becomes a quantitative quality of the little tennis ball or whatever it is.
yeah. Like, because you have, with a tennis ball, it's very clear. You can hold it, you can press it, you can move it, you can throw it. There are entire experiences which are all completely grounded in, your understanding that you can do with it. But the moment, say, for instance, you see the, a light from a flashlight going this way and that way from a mirror, and you start thinking, oh, that's like a bouncing of a tennis ball. At that moment, you have stepped over from observing what really is to making a model of things. And why did you make that model? Because you're extremely comfortable and you really understand the mechanics of a tennis ball. You feel like you've got a grip on it. Now you want to transfer that grip to a different field. And it may win points on convenience, but it loses enormously in terms of really understanding things. It creates like a fog. And people kind of labor under this fog, sometimes for centuries, before they figure out, wait a minute, that doesn't work that way. So instead of putting all this time and, making all these assumptions and only to have to tear them back to various levels later on, why don't we just drop that whole method and try to figure out how we can get the coherence of phenomena in its entirety? wait till we can see something from multiple directions, multiple experiments, multiple ways, maybe over a few years, and only then dare to perhaps venture one guess as to what the idea it could incorporate. I think Faraday was very good at this. Faraday was one of the scientists who was extremely disciplined this way. And Newton said that he doesn't feign hypothesis, but Faraday actually did it. And he struggled a lot before he could name something. He took some things for granted, of course, in that environment of the UK Islands, but many aspects of electricity, he was extremely cautious that he does not try to prematurely conclude something when it's actually something else. So I think we need to be able to go back to that and not kind of fall in love with our equations so much and our models so much, and go in the road that he opened. So that's kind of my work. I'm trying to do that.
I mean, exploring this through the lens of gravity might be a good entryway into it, though I do want to get to the physics of color. So, and the reason that I think that it's easier to talk about gravity than the physics of color, because with the physics of color, you start to immediately get into the soft squishiness of biology and perception. And then you have multiple classes of model interacting. But with gravity, I feel like it's
You
fair
have
to
a handle on it.
at least a little bit. At least a
Yeah.
little bit. So
Yeah.
maybe we can talk a little bit about what it means to understand gravity without having a model.
So one of the remarkable achievements historically have been Kepler's laws, right? He identified, the relationships between the planetary time periods and what is called their distance from the sun. So that relationship, which was, at the same time as Galileo and Kepler were kind of contemporaries. And after that, several decades after that, when Newton comes along, the discussion was still in, very much in vogue. And people were still wondering um, how this all works and what does it mean that you have planets going around, what's going on. All of these questions were bubbling up. And I think what Newton said was, I can derive that. I can derive Kepler's laws straight out of mathematics. And of course, he was challenged and so on and so forth. But then when he wrote the Principia, his classic work, he actually tried to do that. He tried to show how the inverse square law actually leads to Kepler's laws. That was one of his big selling points, that look, my ideas are valid because I'm able to derive Kepler's laws right out of what I'm calling as gravity. So then the kind of crazy thing that got brought into all of this is the comparison between the mythical story of the apple falling with the movement of the moon. So he compared the two, which is truly not something that you will compare at first glance, because apple falls straight down. You do not see the moon fall. So perceptually, they are very different qualities, yet he combined them. How did he combine them? He said, well, I'm going to take what is happening with the movement of the moon, and I'm going to see in the limit what would happen to that if that movement was vertical. Just making that circle or orbit, circular orbit, into an ellipse and into a line. And then the movement of that is similar to the movement of the apple falling straight down. So this is like the heart of the Principia as far as gravitational understanding is concerned. He's trying to compare a circular motion with the linear motion. And the way he's doing that is he's compressing the circular motion into a linear motion and saying, what holds for this also holds for this. Okay, well, as an idea, we can follow that much, but there is a big problem here. And the huge problem is Kepler's laws talk about areal velocity. That means the areas that have swept out by the planets and in unit time. And he says the areal velocity is constant. So if that's the case, that's an observation. It's an empirical observation. What is the area of a line? 0. So when you take something which is the mechanics of which are being described in terms of planes, in terms of orbits, in terms of circles, and you squish that to a line, you're changing a lot more than just a few thought models. You're actually changing the whole story completely. You're dealing with 0 areas, which in turn means the time also has to shrink to nothingness. So that's a contradiction, because things don't fall instantaneously to the ground. And neither is it true that you have anything orbiting vertically up and down, because nothing goes straight through the center of the earth and comes out the other. And all of that is more of a science fiction idea than it is in any way connected to reality. So in terms of reality, you see the circle, and in terms of reality, you see the falling object, but you don't have a bridge between them. And Newton tried to create a bridge by just eliminating one dimension. He just said, you know what, I'm just going to treat them both as the same. And you can see in a few propositions right in the center of the Principia, as he squishes this and he makes things work in order to fit what he requires. So from there, you have this whole generation of the inverse square law, because what he did was he took a law which said r cube is proportional to t square, right? That's Kepler's law. He was trying to get at it from acceleration. What is acceleration? R is proportional to t square. So the distance is proportional to the square of the time. So that's acceleration. So how do you relate r cube is proportional to t square with r is proportional to t square? There is an r square that is different from one side to the other. That's your inverse square law. So he took acceleration on one side, he took Kepler's law on the other side, and the difference between them is the r square factor. So he said the acceleration is 1 over r square, folks. The acceleration is 1 over r square, and therefore you have the Kepler's law. So you have this mathematical gymnastics that take place, and what you end up doing at the end of the day is you end up conjuring up almost a fantasy at the core of physics, where you are hypothesizing that the behavior of the planets is almost exactly like the behavior of an apple falling down. So that's the story of the birth of that idea, and everything after that, whether or not it's a pulling force, whether it is this way, whether it is that way, it becomes kind of immaterial, because what you have is you've taken Kepler's laws, put them in the language of acceleration, and then you start writing equations with that, and then you start calculating with that. So as long as Kepler's laws are valid, your equations will be valid. But what people don't realize is there is a conceptual chasm in the middle that you just cannot cross if you're staying true to the process. But then it accepted, and it becomes a permanent part of physics. So that's
another thing that he did that's kind of interesting is he scaled Kepler's laws with this concept of mass for the first time, and mass became a really important factor in this whole conversation.
Yeah,
which is really interesting, because you might say, what's mass? And well, it would be nice if it was just the number of atoms or something like that. But it turns out that different atoms have different amounts of this mass stuff. And so there's basically a nebulous term. There's this mass thing that somehow changes how attractive the atoms are to each other, but we don't really know why. It just seems to be the case. But it gets wrapped into the mix to the point that people start referring to material bodies as masses, right? It's almost like that's the defining quality, but it's still very nebulous at the end of the day. What is going on with this mass stuff?
Yeah, because what happens is, at least in terms of Newton, the mathematics that was used was predominantly geometry. So you have, distances, angular relationships being the sum total of what was required. But then later on, when this tennis ball thing kicked in, then you can count those tennis balls. And every count, every numerical relationship can be plonked right back in terms of numbers of the tennis balls or numbers of something. So the numbers start entering in and they become counting imaginary objects many times. But the experiment will be showing you a number, sure. It will show you this much of this gives rise to that much of that. So there is a numerical relationship that you can get out of there. But then in your mind, you think it is that many units of these little things is related to this many units of these little things. And therefore, those little things become part of your worldview. And you start carrying that forward now, bolstered and fortified through the power of numbers and the whole strength of mathematics behind it. So it's hard for somebody to argue with the numbers, they say, right? So the theoretical things kind of get pushed by the wayside. Yeah.
And I mean, that is the strongest argument that people raise, which is that the math does work out and you can use the Newtonian equations to predict the motion of objects and launch satellites and accelerate them around other planets and send them off into interstellar space. And so what is the significance of this theoretical step being muddled if the numerical outcome seems to work out?
Well, I think it's before we even get to the point of how it relates to the cosmos and the celestial mechanics, right here, one place where all of that got introduced immediately was in the picture of the atom, because what was done with the Newtonian worldview was kind of funneled straight into the mechanics of the atom. And of course, it's more electromagnetical in the ideas. And right there, you know that there are several odd situations that arise, which I think arise because we have not paid attention to this conceptual issue in mechanics. So it kind of carries over into electromagnetism. I'll give you an example, like simple things. If you take like charges, right? You have two balloons similarly charged. You try to bring them together, and they kind of push away. Simple. Now you have the observation that in matter, all the electrons are supposed to be hovering around the proton, around the positive charge. So suddenly these electrons are not going to zip off from each other as the balloons do, but they're all going to stay within that vicinity. And then the protons also don't zip off from each other. They also stay in each other's vicinity. And then, of course, the later quantum stuff, like they don't even zip around properly. They are all jumping, but then even though they're jumping, they're still fuzzy wuzzy. And so you're completely lost at this point because you have no idea what's going on. All mechanical intuition is out the window, completely out. You're hanging on to a few equations, which is like straws, and you're grasping onto them and hoping you'll get some idea of it. I think this whole kind of situation arose because we missed that aspect of the error that kicks in when you make something rotational into something only linear. You end up creating problems, cascading problems further down the line. And so you have very contradictory ideas getting cobbled together later on. And so people don't see the thread, like, oh, this leads to this, leads to this, it goes into here and becomes this, but then it creates a problem. They think this is a separate problem, and that's a separate problem, if at all it's a problem. And that, I think, is a bigger issue, because whatever happens in the celestial aspects, Kepler's laws are empirical. There is no argument with them. You have what you have. And whether you express it in inverse square law or you express it in some other way, it doesn't really matter at the end of the day, because all you're doing is in an organized fashion carrying forward Kepler's laws to everything else. And of course, even there is an issue. Like, as soon as they started putting the Kepler's laws for galaxies, there was a big problem, because it no longer followed that whole r cube is proportional to t square thing. It did not. So galactic rotation became a huge problem, and now you're saying, oh, wait a minute, what's missing? We have missing mass, we have this, we have that. So the panic kicks in, because
So we'll just go. We'll put together a huge search for the missing mass. It's got to be there. Because the model is so robust.
Correct.
That it must be out there. Even if we can't see it, we assume it's there. That's the interesting thing. We'll even assume it by inventing a magical substance.
Correct.
We'll go that far.
We'll go that far.
As to, rather than go back to the initial assumptions about the model. That is really, really interesting.
And it's a magical substance that creates force, which I think is at the heart of this Newtonian confusion, because Newton created the equation of the inverse square relationship to quantify the force of gravity. And when he feigned no hypotheses for what that was, and he basically said that it was sufficient to describe. The experimental philosopher's job is to describe. Faraday picks up on that, because Faraday, for his explanations for electromagnetism, turns to the Boscovich atom, which is not a real atom. It's this mathematical point in space surrounded by force fields that can be described, and the ability of molecules to bind is basically the compatibility of the different force fields around these mathematical points to lock together or to repulse one another.
Yeah, I think you're exactly right. That is what Faraday did, and it's an interesting coincidence that he was not a mathematician at all. He was very much just allowing one experiment after another to build up his entire understanding. So he did not introduce anything in there which didn't belong, and that's why he was sticking to the force fields, because you can actually see something get pushed off or pulled in with all of the electromagnetic experiments. So as long as you're staying with the forces themselves and the lines of force, as we call them, you're still in something real. You have not created a model of anything. You're simply describing what is. And that's how he was able to, I think, stay grounded in an invisible world, which is a remarkable achievement, which is not enough appreciated. It's like you send somebody who's blind into a room, and the man manages to map out the entire room with almost 100% accuracy. And that's a remarkable achievement for somebody who's blind. And we are blind.
It's almost like he maps out what he experiences in the room. I took 5 steps and smashed into something. Something like that, because Faraday's fields are really just a sea of measurements at the end of the day, right? He's not actually telling you that it's a room. He's just like, look, you go this far and you're going to hit something.
Exactly.
You need a model to come up with the idea it's a room. Like, a room is a model of all of those experiences at the end of the day.
Well, he tries, right? Faraday, when discussing electricity, attributes it to a tension or a torsion within the material. But he's never actually able to demonstrate that there is a torsion within the material experimentally. And so at some point you see him abandon it.
Or what the material is, even.
Well, he actually thinks that the wire itself contains torsion, because he's a chemist, and so he accepts that the material is made of atoms, and purports that the electrical force has to be a torsional force within the atoms of the material, but he can never come up with an experiment that actually demonstrates that there is a torsional relationship. And so he kind of, at some point, he's like, it's the only thing that makes sense to me, but I
Right.
can't measure it to show that it is there. And so I leave it at this theoretical place.
Yeah.
And someone has to figure this out. And no one ever does.
Yeah.
Really.
Yes. Yeah, it's remarkable how much he did, but yeah.
And so,
God, I wish he was still alive
I
to
know.
throw some ideas in his
you
lap.
could get like an AI model of him.
Well, it seems like what they were lacking was a basic conception of the atom. I wonder often how many crises we'd be out of if those people had had access to the, atomic orbital ideas that we have today, and the basic structure and excitation, and really, I wonder if they would have actually come up with a good material explanation for some of these phenomena had they known all of that.
Perhaps. I mean, it is interesting speculation to go into. I think one of the aspects of the discovery of the atom that is not, again, adequately recognized is how closely tied it was to the behavior of electricity. So, for instance, I tried to describe this in my paper on atomism. When you go start looking at what is called an atom, right, from a long time ago on into the modern scientific era, and you see that many of the qualities that they tended to attribute to the atom start falling apart. And one by one, right? The first you have, the very nature of the word atom, not breakable, atomos, you cannot cut it. So it's if it is uncuttable, then how do you explain how it can generate electric, radiation, as they found out? And then how do you account for its other behavior, like the gold foil thing? Once again, you have charge particles. People focus on the particles, they forget the charge. What was actually put through with the alpha radiation was actually you put charge through a foil, and that charged behavior leads to this notion that everything is empty except this tiny little spot. So is that because it is how much of it is what it is, and how much of it is because we are probing the nature of matter using electricity? And then, of course, when you start looking at what are called elements, that kind of comes towards the same subject from another direction. How do we distinguish, say, the different elements, and we call an element, and we say, okay, it has a specific atomic structure, is how we finally landed up. But those elements were discovered through electrolysis. Electrolysis, for the most part, throughout the 19th century, I would say, was one of the key ways in which elements were discovered. So the nature of discovery is implicitly tied to the nature of electricity. It's like that's our measuring rod. That is going to be the lens through which we define whether or not something is, the same material or not, the same element or not. Like carbon, right? You have a diamond, you have graphite. To any person which is like looking at the world and says, wait a minute, that's a totally different substance, this is a totally different substance, I can write with this one, this I can't even put a scratch on. So you have these completely different worlds coming out in carbon, but they're both carbon. And the reason we even call them both carbon is in the electrical and chemical behavior, you see the similarities. So, and even chemical behavior was determined through the batteries and going back into the electrical theory of matter. So the electrical theory of matter fundamentally shaped our path to the atom. And even when you use the electron microscope today to see all sorts of fancy structures, something that you may forget is the fact that electricity is your measuring tool. And by nature, it is one-dimensional. Electricity it doesn't have expanse. It acts as a line. It only, like a lightning strike. You only see a series of jagged lines. So electricity is fundamentally something that acts as a line, and where it encounters a resistance, where what happens when two lines cross? You have a point, and that point is what we call the center of the atom. So whenever we look at it from a slightly different point of view, you say, oh, that's what is there. You have an atom sitting over there, but if you pause, you say, okay, wait, that is the view of the world that I get if I decide to use electricity as my measuring process. If I decide to use that, that's what I will see. If I decide to use something else, I will see something totally different.
What is that something else, though? Because you said earlier that we have this kind of false sense of the world being electrical.
Yeah.
And now I see that you're tying this to the idea that we use electricity in order to study the world, and so it has given us this sense that everything is electrical because our hammer is electrical, all the
Yep.
nails are electrical, everything
Correct.
is electrical.
Yep.
But are there other ways to
Yeah.
comprehend this?
Of course. So, for instance, if you just take the very tiny step from electricity to magnetism, right? Already you see that magnetism is not always tied to an electromagnet. So what they did was, during the process of playing around with electricity and magnetism, they figured out, okay, if you have a coil and you pass current through it, in the middle you have magnetism, and that is interesting, very good. You have magnetism, but that is different from saying all magnetism, therefore, is nothing but an expression of coils of electricity. You see there is a distinction there, because what has happened is we have almost internalized this idea that any magnetism that we see in any substance is nothing but effect of its electronic whatever. They look at they look at the orbitals and they say these are half-filled orbitals, so on and so forth. There are various descriptions of it. So it's an entirely electrical way of looking at this process. We've not teased apart situations where the conditions are very antithetical to the existence of electricity, but still magnetism continues to exist.
You're talking about like paramagnetism and diamagnetism.
And the very question of permanent magnetism. I mean, think about the simple fact that if you have an iron core to the and you put it inside the coil. You take an iron piece and you put it inside a coil which you're electrified, and suddenly the force of that magnet amplifies itself. Okay, so then the question is, in nature, you don't have things where something simply gets magnified. You see, because normally whenever you introduce a new element, kind of an equal and opposite resistance to its entry, it's very difficult in any process to multiply the effect. If we could multiply every effect, then there would be no energy issue. There would be none of the issues that we have today. So multiplication is a very tricky business. And yet here, almost through magic, the very fact of you introducing an iron piece into that coil, suddenly you have increased the energy of that little electromagnet or that coil. So right here, you have to ponder, wait a minute, is it something that is intrinsically a different form of energy that you're introducing, which is not encompassed by electricity alone? That's what we have to look into when we look at magnetism. And so you see this interesting kind of relationship between electricity and magnetism when you heat things, right? So electricity is generally something that works very well when you don't have that much heat in the system. But then when you have the magnetism, you have its interesting property as well, where magnetism is destroyed when there is excessive heat. So when you look at that, that's not the way electricity behaves, because when something is molten, it conducts beautifully. So when you look at the effect of the state of matter, when something solid versus something is liquid, electricity loves it. It just slides right into it. Like, okay, it's molten this, I'm going to act full-fledged. Magnetism, on the other hand, you try to heat something and melt it, it's gone. It's completely antithetical to what you would have had with electricity alone. So these belong to part of what I call that kind of coherence of the whole field. You cannot like prematurely jump on one particular thing. You had an electromagnet, you had a coil, you got a magnetism, yay. Magnetism is nothing but electricity. We got it. We know what it is. No, explore it in all its phases. See its character in the whole drama, and then you can figure out who the character is. You don't get it with one scene.
I think I'd be a lot more comfortable with the electrical explanation for everything if anybody on Earth understood what electricity was in the first place. Like, why a positive charge likes a negative. What the hell is a charge, for starters? Why do they like each other so much? Right? It's just, it starts with this piece of magic, and if you accept that, then you can listen, and there's all this, ostensibly useful equations you can derive, technologies you can build. But at the heart of the thing is just this utter mystery of what in the heck is going on. What are these atoms or whatever? What is this material doing amongst itself in order for this phenomenon to take place? And I feel like if that was an open topic of inquiry, then the downstream effects would be easier to swallow in terms of looking at what is going on, because there's probably some shared process. Like, I'm going to use the word atomic, but let's just say material process at the heart of each of those. If we were really to understand what the atoms are doing, my favorite example, I won't waste too much time with it because I've mentioned it a million times, is the heat theory of gases, right? And they used to be looking for this fluid thing, kind of like the electrons that were called caloric, that would flow through the wires, right? And it didn't work out eventually. And actually, it worked out pretty well. It worked out really well mathematically. Engineering-wise, the fluid flow equations worked perfectly. But it wasn't until somebody had a very different idea, which was, wait a second, what if it's just the molecules moving around, jiggling, vibrating? Then they were able to see this heat business as a very different matter. And I think that same conceptual level revision needs to be imposed upon electricity at some point. Because we just have these placeholders right now, positive, negative charge. They're just magic, right?
And I think maybe to tie it back to what you were saying earlier about models, this is the danger of having a model where you're like, well, it's like a tennis ball, or it's like a fluid, or it's like a force.
Yeah.
Because what you've done is you have taken some phenomenon that you can wrap your head around and have made the analogy sufficiently stable that you can move on from the question and
That's the hurtful part, right?
Like
Moving on from the question.
Yeah, like you fully obscure that the question remains by creating a model in which you can have enough certainty that you're like, no, we have it figured out. And then you start asking around like, well, what is charge? And people are like, don't worry about it. Like negative and positive is enough.
Yeah. I think the magic remains, yes. And at the very minimum, what we have to be able to do is to take the processes and describe them without reference to a model to an adequate level. For instance, what you just said, right? You spoke about the whole vibration aspect of heat, and the phlogiston earlier was one of the ways in which people were trying to figure that out. And it's very interesting to read this paper by Professor Hasok Chang, and I would suggest you take a look at it if you haven't already. And he looks at the phlogiston and tries to see what it was that they were actually observing and what do we make of it today. And he finally comes to the conclusion, I may be oversimplifying a bit here, but he says what they were actually trying to get at, they were trying to get at the electron before the electron was even a thing. So it's not just this bad boy of physics who just misbehaved and it's a lesson to everybody not to be like that again. No, they were actually honestly trying to describe what they were seeing, but electrical theory was far in the future. They had not yet gotten that far in order to be able to grasp that critical point. So, of course, when you write a history, you say, oh, you know what, we were completely off with that one. It will just throw the whole thing out. And, well, yes, but don't throw out the baby with the bathwater. Observe what they had observed. And then you can move forward, right? And the same thing with the heat thing as well. Like when we speak of a vibration, this was one of the entry points in my own life towards this whole way of questioning physics was precisely that. Because when you look at vibration, a vibration by definition has a midpoint. You have a pendulum, or you have something else, a back and forth, and so on and so forth. You always have like a positive, a negative, and a midpoint. But when you heat something, it expands outwards. Why do the midpoints get displaced outwards? If all the forces are what they call conservative and everything is symmetrical and everything except the boundary of an object is pretty much symmetrical, there's a push this way for every push that's that way. So if every push this way and every push that way exist in the material according to the vibrational idea, then why aren't they canceling out and you just get an increase in temperature without any expansion?
I guess it's all these I always figured A, it's due to the container, and B, the elastic collisions amongst all of these materials, right?
Correct. But there is a symmetry problem because it's all symmetric. It's symmetric in 3 dimensions. Every push, like a vibration, however you call it a vibration, if it goes this way, there is a backward in whichever direction. So the very idea here, you see the model kind of creaking a little bit, and then you say, okay, you have a vibration, wonderful, but then you have a displacement of the whole thing. There's a rising like a dough. Why does something expand when heating? So I ended up asking my professors this. I went to my thermodynamics professor back in undergraduate. I said, hey, I have this equilibrium issue. How in the world is symmetric vibration creating an asymmetric expansion? How do you get this
Are
from
you
that?
thinking specifically of a case where you have a metal plate with a hole in it where it expands outwards and the hole diameter also expands outwards, as opposed to there being... Because
Yeah,
it seems reasonable that if you have a plate with a hole in it, that the plate would expand in all directions equivalently, and so the hole in the center would shrink, but it actually doesn't do that. Everything expands outwards.
yeah, it's a photographic expansion. It's like a scaling process. You just have you zoom in or you zoom out. You're not actually changing the relationships between the things. That's remarkable. You're actually not changing the relationships between the things, and yet you have a change. So when I was digging into this, well, it was almost like the story of Kafka and his castle or something. If you just get shunted from one department to the other. So I went from the quantum mechanics guy, the thermodynamics, to the quantum mechanics, to another guy in just plain mechanics because we wanted to look at the vibrational aspect, and then chemistry and what's happening, statistical mechanics. Yeah. So it was just a round robin because they had not thought about this part. And it's right there staring us in the face. And so these are the kind of things that point to us like, wait a minute, your model may collapse pretty quickly. And then, of course, you have this problem that occurred later on. Like, wait a minute, heat is something that is propagated through vacuum or vacua. And then, so there is no material substance, and yet you have a transmission. So what's happening here? So then you land in trouble there too. So it doesn't work fully for the substance, it doesn't work fully for the vacua. So what do we have at the end of the day? It's not so simple. So it is possible that even heat, we cannot simply reduce it to something else, like motion. You're not trying to describe electric charge as a vibration of a particle, right? We take electric charge, that's like a fundamental anchor. We take charge as is. We say it's a property, we're not going to worry too much about it, but this is how that property works. But with heat, we say, okay, heat is this, but it is like a modification of this property of a particle. So we have got this, derivative property of heat, whereas electricity is more fundamental. It is there and it is there, and that's how it is. We are not trying to describe, oh, is electricity a form of heat? We're not saying, oh, is electricity a form of motion? Is electricity a form of mechanics? Like we're not doing that. We're sticking to that. I think we have to follow that process for all the different things. We have to follow that process for heat. We have to follow that process for light. We have to follow that process for magnetism. We have to follow, that process for the different properties that we see, entire fields of science that we have to deal with. They all have their own reality, and you can get to that without obfuscations.
But you still have to tell a story at the end of the day of what's happening, right? Even if it's provisional. I think that the story is the basic unit of human knowledge transmission. If you want to relate something to somebody, you have to tell a story. And that's where models become so attractive because, it's a way of telling a story that makes sense, hopefully, and includes all of the observations, hopefully, and becomes satisfying. For me, the problem becomes when you start believing the model is reality. That's when I see things go off the rails. But I'm quite a big fan of making up models for how things happened. And I could be, I'm open to having my mind changed about this, but I find it quite useful in terms of my everyday life, trying to problem trace how different things went wrong or whatever. I like to make up models and pit them against each other and see who comes out on top.
I think that it's just maybe epistemic humility. It's being able to say that there is still a gap in the understanding and the model is incomplete. It's not like a tennis ball. Our best sense is that perhaps in some cases the particle behaves like a tennis ball, but to end our understanding and our search on the idea of tennis ball as the final model is where we run into problems.
And even by calling it a particle in the first place, you've already kind of made it a tennis ball.
Yeah.
It's like that word, there's all these words, right? Charge, particle's another one that we use it all the time in science. Yeah, there's so many of these words, and you think they mean what they mean in everyday language. Like a particle for people on the street is just a chunk of dust or something, right? Yeah. That's not what we're talking about here. I mean, these particles have intrinsic momentum. They're obviously a process that's happening of some sort. There's activity, in other words, motion inherent in these systems. Yeah. They are predictable observations, you could say. They're predictable measurements. They are oftentimes measurements themselves. They're interesting patterns, but in my mind, we've already gone off the rails when we start calling them a particle because they're not. It gives the wrong picture to what we're dealing with and perhaps limits our solution set.
And in terms of the picture of what we're dealing with and limiting our solution sets, like I feel like one of the things that, and you can, you contradict me if you think that this is barking up the wrong tree, but I think there's something significant about the eradication of the ether as a plausible mechanism for the transmission of anything. Because whereas before, at least there was a substance that filled the space between atoms and was the medium of transmission, now you have removed it. Einstein introduces space-time, which he calls a non-kinematic ether. And so to me, it sounds like what I puzzled over this for a long time. And I I think that at the end of the day, what he's trying to say is that it is not an ether that can act independently. It's an ether that can only be acted upon. Like, I think that that's what he means by non-kinematic. And so he provides a path forward that is non-luminiferous ether. And in so doing, we have completely erased any part of the model where transmission is happening through something. Like we say, heat energy can transfer through a vacuum. And it's like, okay, well, how?
By radiation?
By radiation. It's electromagnetic radiation. What is electromagnetic radiation? It seems plausible that it's the motion of atoms. And so if it's the motion of atoms and it can transmit through a vacuum, and we know that there's vacuum energy, then perhaps what the vacuum energy is it's this non-kinematic ether that can actually be detected, that is the communion between the atoms at distant places, and all of a sudden heat makes sense because it's still motion on one end, being transmitted in the form of this specific type of radiation that is transmuted into motion on the other end.
Right.
But without the medium, if you're like, no, there's nothing there, it's just the vacuum, it's
That's
empty.
the craziest leap of all for me, is that the medium they were working on didn't work out, and so they're like, well, no medium.
Yeah,
That's such
what
a
happened?
bizarre, unscientific thing to do. Like, I
Yeah.
can't believe that people are proud of that,
Yes. Yeah. You can't be proud of a cop-out.
But they are. It's
They're
so
very
bizarre
proud of
because
it.
the mathematics is so powerful, right? They're like, no, like general relativity, we don't need it. I'm like, yeah, but it doesn't make it go away, right?
Yeah.
I understand you don't need it for your GPS or whatever it is, but that doesn't solve the scientific question. And it's so strange that people just very triumphantly and dedicatedly walked away from that problem.
Yeah, do you have a sense of the time and what permitted that? Because we always
Like
looked
at least with charge, we go to our professors, when we're in grad school, and be like, "What is charge?" And like they'd be annoyed with us because they're like, "It doesn't matter," but they're not like,
Yeah.
there is nothing, right? They're not like there is no answer to that question. But with the medium of electromagnetic radiation or gravity or something like that, they're literally like, no, that is not an answerable question. That is not a question that we deal with. It cannot be answered. It's not even a question you should be asking.
What kind of, because you have the quantum field. But the quantum field is really weird because the quantum field is a sea of either vector or scalar measurements. And when you're like, okay, well, what are those measurements? They're like, no, there's nothing beneath it that generates the measurements. And that, to me, that's even weirder because they're admitting that there's
I think it's same as medium being off the table. Because the question cannot be asked in the current conceptual framework. It breaks the computer.
I think that it's even deeper than that because it's not quite like dividing by zero. It's almost where they're like, no, the numbers are the thing.
Yeah.
And I'm like,
the thing.
How did that
happen? Which is a computational worldview, right? I think that gets us back to the computers, right? Where that's the only way we conceive of information processing and transmission of information is in this computational basis where you either calculate it or it doesn't. That's it. Just calculate it.
Yeah, so let's see if we can unpack this, because we always tried to pin it to Michelson-Morley.
Yeah.
But that seems too simplistic because Michelson-Morley is just one experiment. When in the history of science has one experiment served as being the place where everybody's like, okay, hey, time to wash our hands of this question?
I think there was a lot of different interferometer experiments around the same time, people reporting nothing that was consistent or fit with this plum pudding type ether.
Yeah.
But yeah.
Yeah, I think that whole social process is very interesting also because I have read it somewhere, I don't recollect where exactly, that the attitude of the scientists at some point started getting mingled with the attitude of a lawyer. So the way it works is this way. So when you look at a law setting, you have this one critical, crucial piece of evidence on which everything turns. It's that mode of looking at things, and where you have to prove this and you have to prove that and you have to argue for this and argue for that. In many ways, scientists have kind of subconsciously soaked that up. I mean, since the time of Newton and the experimentum crucis, the one thing, the one experiment that illuminates everything, the most critical one. I think since that attitude kicked in, then the fighting for the models also becomes part of it. Because now you're trying to prove your theory, and the other guy is trying to prove his theory, and you're almost battling it out in court of public opinion or made up of scientists, right? And so that whole philosophy, there is a mismatch between science and what we are supposed to be doing. If we want to be doing science, we can't be doing law. I know we are dealing with physical laws, but this is a different domain. This is not about argumentation. This is not about preponderance of evidence and this one critical evidence and all of that. It's about reality and how best are we able to, you know, encompass the whole truth of the matter to the best of our ability. That's what it's all about. So in this situation, I think when this other thing kind of hits you sideways and this lawyer mentality sneaks in through the back door, then you have this deification of one single experiment, like the one thing. So whether it's Michelson-Morley or whether it is experimentum crucis or something else. So it reduces the entire complexity into that one thing.
What is this experimentum crucis? I'm not familiar with it.
Oh, the Newtonian experimentum crucis, that was the light going through a prism, and then you have a spectrum at the back, and then that light is isolated and it's sent through another prism, and then that goes and deviates at a certain point. And that was the idea, that was the experiment which led to the idea of optics as light being made up of colors. Before that, it was not light being made up of colors. Before that, it was colors being generated because of light interacting with something that can obscure light. In this case, a prism. In some other case, something else. The idea was always, the idea of colors was always dependent on this interaction. But then Newton tipped that over and said, no. Light has it inside. And what we do is like sorting marbles. We sort the red ones this way, blue ones that way. And so that is the experimentum crucis. And it's become a pattern that has been set in science where people look for the experimentum crucis. I mean, I wouldn't want to completely devalue it. Of course, there are critical experiments which kind of tell you whether you have to go this way or that way. But to throw the entire weight of a whole worldview on one experiment is just putting a bit too much on top of it. And if you do
Yeah,
that, then
I think the thing that you brought up about the zero sum nature of it, where you have to have a clear winner and loser, I think is really where things go off the rails. It's anybody who's really dedicated, or if anybody has any friends who are lawyers, it's very clear that some people can win an argument without being right.
Correct.
And that gets into really sticky territory when you're talking about really trying to understand how something truly happened. Right? You don't want the person with the best argument necessarily to win. You want to really understand nature. And that requires, I think, a real diversity of theory. It requires a lot of perspectives about what's happening because nobody gets it all. There's going to be little... Go ahead.
I want to modify that because I think that you do actually want the best argument to win. You don't want the best arguer to win.
Yeah.
Right? Because there's the person who's the best lawyer.
You also don't want it at the exclusion of all the other arguments too. It's kind of like what I see as being the broken part of our democracy too, is that it's this zero sum game where either your team wins or your team loses. Yeah. But it could be set up very easily where the losing team gets the vice president role or something like that, right? Where everybody kind of wins a little bit, right? Yeah. So you don't just dethrone theories wholesale. You're like, well, wait a second, like let's put this on the back burner. There might be something interesting to this. We should keep it in mind.
Yeah.
And we don't really have the social wherewithal for that in the sciences at the moment. It's very much this competition for winner takes all. And I don't know the way out of that, but it does strike me as a pretty obvious problem, and I'm glad you brought that up.
Yeah.
So
Yeah,
look, I want to talk about colors too.
Sure.
And you want to take a break?
Yeah, let's take a little break.
But is there some bow that we can put on this section of the conversation before we break with this idea of science as law and the dangers of allowing it to become this proof-based winner-takes-all mentality?
Yeah, the one critical thing that happens over there is you don't introduce evidence that opposes your theory. Where does that go?
Oh, well, that's the opposing counsel.
Yeah, yeah, that's the thing. That's if they
Last
don't
minute
pick up on
affidavit.
it. If they don't pick up on it, then you've lost it like forever in the process. Like, you may know about it, but you won't show it because the other person can turn it against you. But that piece of evidence is part of the truth. It's part of what you observed, say, in some experiment. And revealing that would have made you lose that argument, perhaps, but it would have forwarded the knowledge, our collective knowledge, much faster. It could be critical in a way that you don't even know. So that gets lost. I would say that is the one of the bad side effects if we go to science as if we were doing law. We end
Yeah,
up.
I mean, I think a really great example of that is the germ theory of disease. The Koch's postulates, the 7 things that define the biological entity that causes disease, were disproved within a few years of him putting together the list of things. But it's taken us almost 100 years to get background to the idea that there's more to disease than simply the microbe. We had to go through the entire era of overuse of antibiotics, of treating disease as being something that comes exclusively externally as opposed to being a mixture of environment and terrain plus microbe.
Yeah.
And it just takes forever. It's exactly as you said. If these things are obscured in service of writing something up that's very neat and pretty and complete,
Correct.
the neat and pretty and complete thing is the thing that our minds latch onto. And then the other portion of the conversation we just have to pray and hope that somebody will one day pick up on it again.
Yep. Exactly.
That's really fascinating.
Yeah, that's all I wanted to say on that. Yeah.
Okay, well, let's take a break. I was laughing because I was looking at there's a Stack Exchange thread where somebody asks if they were standing next to a piece of metal heated to 1,000,000 degrees in a perfect vacuum, would they feel hot? And somebody offers this quantitative calculation where they explain just how much heat they would experience in the X-ray range, and answers the question of, would you feel it? I'm not sure, probably only very briefly. There's
10 to the 16th watts per meter squared. 10 trillion times the power a person on Earth would receive from the sun if there were no clouds and no air. Yep. But yeah, radiation.
Yeah, I hope that Stack Exchange manages to survive the AI replacement.
What manages to survive?
Stack Exchange, the place where people
Stack.
would like the forum.
Yeah. Physics Stack Exchange. Got it.
Mhm.
Yep.
I don't think an AI could offer such a glib response.
Yeah. The entertainment value alone is very
Yeah.
good. Yeah.
So where do you want to take us, Delay?
Yeah, let's so I didn't totally understand, or maybe you can clarify what you're working on with the color situation, because colors from the Newtonian perspective, components of light, well, of course we end up with waves of what, but something is waving electromagnetically, and there's different periods and wavelengths, and so we get color. What's the alternative?
Yeah. So in the creation of that idea, you have 2 or 3 layers. The first layer is, of course, this idea that colors exist in light and they have to be parceled out. And one of the effective ways of doing that is using a prism. That's one layer. Second layer kicked in with the whole idea of alterations of dark and light, which was then the wavelength idea. So that's the second layer. And then the third layer is because of the rise of electromagnetism and finding out the relationship between the speed and so on and so forth of the light speed matching what was observed in the electromagnetic experiments. So then everything kind of locks in together, and we have what is the modern way of looking at light. But if you go back and start observing some of the things, again, some of the pieces of evidence that don't fit the argument, what was observed almost immediately by those who were trying to replicate Newton's experiments was, these colors which you say are separated out. I'm not getting that. I'm seeing that further down the line, if you put another prism and you pass a color through it, it's again giving rise to more colors. And it doesn't matter what I do, it doesn't matter how narrow I make it, I'm still getting colors out of it. And Newton's answer was, no, you won't get any colors, go back and do it again. Kind of thing. But like even today, you can show that through experiments. So it's like, okay, so number one, right at the very beginning, at the fundamental basis of how we say color arises, it is not as parcelable as you or like piecemeal thing that we assume it to be. Then you also had this situation about colors that don't exist in that spectrum that he got with the prism. For instance, have you guys noticed the oil patches on the ground when you have rain and car has some oil leaking and stuff? You have these brilliant colors, and you also
Very
have
beautiful.
those. Yeah, absolutely gorgeous. They're also in the soap bubbles. You see, sometimes in thin soap bubbles, you'll see these colors. And one color that you don't see in the spectrum but exists in wonderful vibrancy is magenta.
Hmm.
So, what's the deal with magenta? So what happens is when you look at the Newtonian spectrum, there's no magenta there. But if you invert the conditions of Newton's spectrum, so what does that mean? If instead of having a light beam coming in a dark background and going through a prism and giving you a spectrum, instead of having that situation, if you flip it, in other words, you have a brilliant field of light, and instead of a slit, you have, let's say, a pencil or something blocking all the light coming in. So you have switched light and dark. Instead of a dark background light coming in through the prism, you have light background and light being blocked. And that is what is through the prism. There you will see a different spectrum. In the place where you had red, now you have cyan or light blue. In the place where you originally had blue or dark violet, that end in the Newtonian spectrum, there you have pale yellow. And in the place in the middle where you would get green, you have brilliant magenta. So this was observed, about a few decades later by this poet Goethe, and he raised a hue and cry about it. And there was also other people who were already examining the Newtonian ideas, and they're saying, "Hey, yeah, not every color makes its way into this." And here I'm having the opposite. Here I'm having uh, the more refractable being the pale yellow, and the less refractable being the light blue, and then I have magenta appearing. And more importantly, they also said, this green that you call as part of your spectrum doesn't even appear until you go a certain distance from the spectrum. It doesn't prop up. Like if you have a prism and you put a screen very close to the prism, you won't get green. You have to keep moving the screen, moving the screen, moving the screen, and at one point, one side and another side will overlap, and then you get green. And the same behavior happens with magenta. At one point, you have an overlap and you get magenta. So, right, you can see the like a what do you call the strict textbook approach already loosening up a little bit when you start taking these into account. And what happened was people were struggling with these ideas, and they struggled through it almost for a century after that. And when folks like Helmholtz came around, the physicist Helmholtz, the path they decided to take was magenta is an illusion of the brain created by your brain. And all the rest are real colors, but this one color is made up. You just make it up. But you see already that number one, it's a cop out. And number two, that basically yanks the rug right out from doing any understanding of color, because you can just throw out all the colors based on that very same argument. You can simply say there is nothing. Everything is arbitrary. There is no rhyme or reason to any of this. Your brain just makes up whatever it wants, and that's it. Pack up and go home. You know, that's the dead end that it leads to. But they don't go there. They instead try to manage both of them. They keep the real stuff. They keep the colors that they have gotten through the Newtonian spectrum, and they keep this field that newly opened up almost at the same time of you know the physiology of the eye. That's when the shift went to the physiology of the eye, because the ideas that Newton was proposing for our understanding, our perception of colors wasn't fitting, and it was kind of coming to a halt. So then they switched over from the outside to the inside. Now this is a very remarkable development, because come to think of it, for other things we didn't have to do this. We didn't do this for, say, electricity. We didn't do this for mechanics. Since when was the last time for mechanics you had to perceive the receptors in your skin and their capacity to perceive pressure as a prerequisite to understanding the science of building a car? No, that was not part of it at all. But in this case, in this special branch of physics called optics, we have decided to go this route. And therefore, you have this notion that color is subjective, and it's all dependent on the person, and so on and so forth. If you examine that idea, you will see how it leads to problems, because just in the same way some people are colorblind, in a similar way some people are paralyzed, some people cannot feel pressure, some people cannot judge distances properly. There are several people who have coordination issues. They see it, but they don't really see distance correctly. And many people who haven't had an operation and gone from blind to seeing, they prefer to go back to closing their eyes because they cannot process the distances, even though they can technically see them. So you cannot use the human variations as a reason to deny the objectivity of something. You cannot say, because there is a variation in how I feel pressure is subjective. That is a logical leap that is fraught with problems. And we have made that logical leap in case of color. And one of the reasons is because we have stuck to the Newtonian spectrum. We missed the other half of the coin. What happens when you have positive and negative kind of switched over? So that's like a small opening into the thing as to the first layer, the experimentum crucis, whatever came up with the Newtonian stuff, and so on. Then there are, of course, the other two layers as well, which are also kind of follow up. The same thing continued through to the other experiments, even in, say, if you have a diffraction grating. We use diffraction gratings all the time. And if you switch the stuff around, instead of having a diffraction grating in a box completely isolated from all the surrounding light, extremely dark, and you don't have anything to see, if you switch that around and you simply put a diffraction grating in a bright open light, whether it's a tube light or anything else, you take out one of those gratings and you plonk it on the table, and you put maybe your spectacles or some dark object over there, and it'll show up in a brilliant magenta, yellow, and cyan right there. That black object in a white lighting will show you a different spectrum. So now you have this, the idea of wavelength, you can link it in two ways. You can link it to a red color in a dark background, or you can link it to cyan in a white background. And green, same way, same wavelength you can attribute to the, as you would do for magenta. So magenta and green will have the same wavelength with the things switched around. So like you have to redo all of that if you were to, make it in harmony with what was kind of left out when Newton first began his investigations. So that's the second layer. You have the first layer with the different kind of colors kicking in, second layer with the whole wave aspect and how we identify colors as having something that changes. And the third layer with electromagnetism, that's another case where I think we have jumped a little too prematurely into calling light electromagnetism and nothing else. And the reason is simple. Experimentally, if you have, what will happen? What would you expect to happen if I have a transparent conductor and I'm looking outside through that transparent conductor? Is that going to change if I ground that conductor? Because if I have a transparent conductor and I'm looking through it, that means I'm perceiving light. If I ground it, and light is electromagnetic radiation, that transparent conductor should work like a Faraday cage. And it should ground out light itself. Have you ever come across a notion where light is made invisible because of electrical grounding of any kind?
Well, not all materials make very good antennas to receive light, I suppose. It would be the argument. So they're not all photoelectrically equal. So maybe the glass or whatever you're using isn't. I mean, you're supposing that it is conductive, though, that it is able to be
It is conductive, yeah.
organized, because it has a lot to do with the organization of the crystal structure, from what I understand as well.
Well, we've thought about this in a different way, which is that there's no current that is so strong that you suddenly start to see optic effects. Like at some point you might see light, if you have something that arcs like lightning, but it's not like you can have a massive magnet and then as you look at it, it appears to shimmer.
Shimmer, exactly.
And I think that's kind of that's a different way of thinking about the same thing, which is that if you have an optically clear conductor and you ground it and all of a sudden there's no current through it, you're saying that it should go dark.
Yep. Or it should be affected. At the very minimum, it should be affected. And so the things that would normally drastically change the electrical behavior and magnetic behavior seem to have very little effect on light as such. But if you pass light through a substance, say like Faraday did, you pass it through something and then you put a strong magnetic field around it, then you have the Faraday rotation of the polarization. So you have a rotation of some kind, you have an effect on the light because of the magnetism, but it needs the mediation of that substance. And that is what is missed. We kind of take that substance off and put everything on the light. It's doing everything. And that's where the old idea of colors and everything coming out, interaction between light and matter is so important, because now you can kind of see where we have been taking relationships as things that light itself possesses. And so what we have done with the magnetism is, once we saw that there is a rotational aspect to the magnetism, we said light is magnetic. Is a very elementary flaw. It's like if I rub my hands two hands together and that ends up creating some heat, then I cannot then go and say, because I rub my hands together and they generate heat, my hand is a modification of heat. But that's what we have done with light.
Yeah, I always thought it was really interesting how light is conceived of as an electromagnetic wave. And you would think that somebody had done the experiment to measure that there's something waving in between the two antennae or whatever optical system you have. But the fact of the matter is just that periodicity scales spatially, and so it's assumed that something is waving in the middle. But the reality is you only have the emission cycle and the output cycle or the receiver detector cycle, and you can correlate them in such a way that the model of this wave in the intermediary works out. But it's not like anybody's looking to see
Yeah.
if there's anything going on in the middle.
Yeah, the alteration is true. There is a periodicity that we see everywhere. There is nothing wrong in that or mistaken in that. But what happens is when we try to say that the alteration is only electrical or the alteration is magnetical or whatever, and that is in turn what light is. So when we start putting these things without cross-checking, then I think we land in an issue. So we have to go through these three layers, right? And the culmination of these three layers, I read in a book on understanding photons, and people were trying to describe photons, and it's like breaking their heads about it. Like, how in the world can I define a photon that is internally consistent? Then finally, one guy gave up, and one professor said, a photon is whatever a photodetector detects.
Exactly.
Yeah. So that becomes your final situation. You have a measuring instrument that once again, so predominantly runs on electrical responses, and that's what you say, okay, aha, I have my anchor here. This I know. So regardless of what light is, I know it will give this signal in a photodetector, and that's what a photon is. So that's the culmination of the whole optic story, starting with Newtonian colors, going through all these different layers, and now we just have to say, you know what, I don't know what light is anymore. It's just what this device
It does this
tells
thing
me.
though, and we can use it to build these incredible magical devices.
Yeah,
That's really we've really puzzled over that argument for a long time because it's a fair point. Like we know how to manipulate it, who cares, right? But I think it's also very deeply. I think I can't get around this other than by some sort of spiritual side to it, which is that it's very deeply disempowering for people to be told that things don't need to make sense.
yeah,
Just
it
because
is.
we know how to manipulate them, well, that's great and everything. But what about just the sheer scientific curiosity of trying to figure out how nature does all that mysterious business that she does? It seems
Yeah.
like we all have a right to know. That's what we are. We're curious beings. And to have the conversation shut down because, well, it works, it just seems a little bit spiritually necrotic to me.
That's a very interesting way of putting it. It's also the thing that for people who say it works, therefore it is okay, they're simply saying when something works, it makes sense to them. And they're asking you to take over that same definition of what makes sense for you as well. It's an imposition of a worldview. Something working is not my criteria. Like, I can use a computer as a paperweight. That does not mean, oh, it works as a paperweight, so shut up and put it on the paper. It's at the most elementary level, something working is a very, very narrow and specially chosen way of looking at the world, which deliberately leaves out everything else.
There's a
Yeah.
values assignment in there, is the
Yeah.
truth of the matter. That's why I just can't help but bring this into this moral, ethical, spiritual realm. I don't know a better word. I know the word spiritual just makes people cringe in the science world, but
Correct.
what I'm really trying to point out is that there's a value assignment there. If
Yeah.
you believe in a computational future, you believe that technology is our savior, then it makes a lot of sense that that's how you're going to look at the world.
Yeah. And then, of course, things are not so working so well in the other areas. Yeah.
Well, there's that exactly, too.
Yeah.
And that brings us to where we began this conversation about the question of science and technology and nature and design, which is
Correct.
that if we really understand how water flows,
Yeah.
maybe we don't make right angle pipes. Maybe we design things that are more reflective of the patterns so that the pipes last for longer. And it's the same thing here. We invent technologies that utilize phenomena that we don't fully understand. We don't realize how they reflect on us. Like,
Correct.
we had this really interesting conversation just the other day with a guy who works on light bulbs. And he started studying the effects of the near infrared on the human body, and he started to realize that our conception of the way that the body absorbs light is kind of incomplete, and that this full spectrum solar sunlight contains with it both UV and near infrared that seem to work in concert to allow the skin to produce all of these necessary hormones.
Right.
And when we had incandescent bulbs went a little bit further into the near infrared, and so semi-recapitulated
Yep.
sunlight.
Yep.
And now that we've...
But they were wasteful, right?
But they were very wasteful. They generated a lot of heat. It was a problem. Now we have all of these LED bulbs, and the LED bulbs are crazy narrow spectrum, and all of the light that we're bathed in is incomplete. And so his proposition is that you have all of these downstream health problems that start with hormonal imbalances and end with, depression and mitochondrial diseases.
Yeah.
And I'm not like buying it wholesale, but I think that that's a great illustration of us not fully understanding what it is that nature is doing, and then designing something for the sake of convenience, for the sake of profits, for the sake of, honestly, convenience and I always want to have three, and sometimes I run out.
Well, now it's about defending the planet, right? Let's ban incandescent bulbs because they're bad for the planet.
Which is also a profit motive of some sense, because somebody manufacturing light bulbs is getting rich somewhere. But the point is that, we make these decisions that are on the basis of some set of criteria.
Values, really.
Some set of values, yeah.
Which is usually efficiency. And then I just feel like the most common value on Earth right now, I feel bad saying this, but the one, at least, I don't know how to be, I don't want to be so totalizing, but it seems like there is a strong value towards efficiency and towards technological progress, particularly electronic, digital, computational technological progress.
And if I am allowed to take the soapbox for a moment, and if we don't fully understand the way that electromagnetic radiation works, then we can never fully understand the effect that it has on us.
Yeah.
And we're bathing in it.
Yeah.
And you think back on the days of the radium girls that are licking the paint brushes with radium paints to paint these watch dials.
Yep.
And we're not there anymore. Nobody's licking radium paint. But you sleep with a Wi-Fi router right next to your head. What does that do?
Yeah,
We don't know.
exactly.
And there's not a lot of exploration of it. And I think that the exploration comes from this basic question.
Yes.
What is it actually?
Yeah.
And how does it create the effects that it creates? And are those limited to just these inanimate electronic bodies that we have created?
Yeah.
Or is a more complete theory of how nature does its magic actually going to feed back onto us being able to design things in a way that is better and smarter and less destructive?
Yeah, absolutely. I mean, you just mentioned that excellent example, which is another aspect of seeing the difference between light and electromagnetism. Look at how we respond to sunlight, and look at how we respond to the Wi-Fi radiation. Our body is answering. The reality comes from there. So on the one, we feel energized, we are healthy, and so on. But on the other direction, you have lots of health issues. You have people struggling from flu-like symptoms when they have been overly exposed to the local electromagnetic field, whether it is their Wi-Fi router or anything else. People are electrosensitive, all sorts of things kicking in. Why this stark difference in the way we respond to electricity versus the way we respond to just sunlight? Surely sunlight has something else going on than what we think is going on in it. Otherwise, all that electromagnetic wave hitting us every single day, it would have had to affect us very differently if it was indeed only electromagnetic.
Yeah.
So,
I found out recently that, that electricians have one of the highest suicide rates of any profession. especially the ones that work on high voltage power lines. And in the literature, people are like, maybe they just spend a lot of time alone and they get really depressed and sad.
Yeah, you can talk your way out of all these. I remember another one too, where people whose homes were underneath those high voltage power lines had significantly stronger all-cause mortality in some time frame, and people were just like, "Well, they're poor. That's why they live under the power lines, and therefore, there's you can always squirm." That's the problem with being a really good arguer. Once again,
Yeah,
it's like,
yeah, yeah,
all right, good argument, but really?
yeah, yeah, exactly. Yeah, and on the notion of argument, and values, one of the turns we took in our evolution in terms of science has been this undercurrent of Baconian philosophy, of Francis Bacon, that treats nature not so respectfully.
Let me take
And
nature by the forelock.
yeah, and basically the atmosphere of the Inquisition probably that surrounded him or what have you. But the attitude was one of wringing out the secrets, getting the confession out out of that thing, and the language is very like brash for us to read today, but that was there right at the foundation of a lot of our science. So we have an intrinsically disrespectful or arrogant or power-based view of tackling scientific subjects, and then it penetrates its way over the decades, over the centuries, and it takes on softer forms, not more subtle forms. You're not outright trying to blatantly say that, but it kind of informs your every micro action and how you do your research, how you do how you come up with ideas, how you argue it out with other scientists, how you care or do not care what happens from the technologies that come out of your ideas, and how the technologists care or do not care about what happens when they put it out there. The same thing which starts right at that root has cascading effects all the way down, and that is really one of the forks in the road where I think we have to take a different path, and scientists have to be also trained with respect to their own psychological traps and their own biases. We never received training on that. I don't know if that ever came up when you guys were doing your undergrad and PhD and everything, but it never came up in mine. We were never taught, what, you can think this is how it is. It may not actually be how it is. You have to be sure that you're not doing it just for, glory and vanity. This is what happened to scientists who did it for this reason. You have to be careful what you put out there because you are responsible for it. If you do it this way, people can misuse it. Like some consideration of the ethical aspects. No, it's this put in that little box. Oh, maybe the social scientists will deal with that. And as far as training goes, you have no inner training at all, no inner discipline, no inner if you're a sincere person by nature and you kind of use that educative experience to continue on that, good for you. But as far as the system itself goes, the course itself goes, it's not going to offer anything in that direction. So that is what I think we require, and when we need to find people who are ready to do that while they're doing science as well.
It's really tricky to teach ethics. There's a meta study recently that looked
You have
at
to incentivize ethics, I feel like.
you have to incentivize ethics because there was a study that looked at ethics professors to see if they were more ethical than the average population. So they submitted questionnaires of, do you cut in line? Do you, steal creamer from the coffee shop? All the way down to, blatant academic dishonesty. And they didn't seem like they were more ethical than the average population.
Right.
And it also seems that when you teach ethics to students, it doesn't propagate into better behavior because the system, you know the right thing to do, but then you go into a system where you're like, well, I need money and I'm going to go work for this company that weaponizes social media to be directed at the brainstem of
Right.
children.
Yeah.
And it's like, I'm gonna make bank. It's gonna be really good.
There's no professor positions left.
Yeah, there's no professor. Exactly.
Yeah.
Yeah, I was going to
Right.
ask you, do you think you seem to have some optimism? So, do you think that the consumers are able to steer the course of technology towards something more humane? Because I do see elements, whether it's the popularity of organic foods or the popularity of different fitness trends, uh, green materials, green building, solar power. People, at least who have significant disposable income, seem to be interested in making the world a more technologically harmonious situation.
Right.
And I wonder if you think that that's enough at the end of the day, because the technologists are just going to build whatever people will buy. But if people are only willing to buy stuff that they perceive as harmonious in the sense that that we've been talking about, will that work out?
I would say partially. First of all, yes, I do think there is a way forward, and there is obviously uh, not a situation where there is nothing we can do and it's all going to slide down. There's very clear things that can be done. And in terms of customers, it is partial, I think, because one of the things that we have noticed just from observing over the last several decades, the user patterns and so on, knowledge defines everything, right? So if the consumer does not know or cannot know or doesn't have the wherewithal to know something, then there is no way to use that in their buying decision. For instance, you may think that something is very good, but you may not realize that that thing that you thought was very good ends up causing another bunch of problems somewhere else down the line. And we have seen that with smartphones and the whole internet and everything. The amount of energy that goes into the data center for a single Google search, it does it even match up to the amount of energy you would use if you were to just get up and look in the dictionary? You see, there is we don't think about these things because it's not part of our knowledge base.
I do
So I
actually think about this all the time when I count the number of tabs that I have open and how many of them are Google searches. Like every time I Google
yeah,
something, I feel a little twinge of guilt.
right, one of the few, I would say. But the other side is the problem was caused top down. And I think to some extent, the solution will also have to come a little bit top down. So the way I see is like what you're seeing is the consumer, he's like literally the last person on the line. Somebody thinks of the idea, somebody makes it, somebody builds it, somebody markets it, somebody uh, then finally he gets it and he uses it, and then he's the last one in the line. And now for a change to happen, of course you can go last to first. You can say, okay, the consumer will push the company will push the scientist will maybe think of a different thing that may go, uh, but I think it's not the same effectiveness as going from the other end. Let us kind of decide on a more healthy philosophy. Let us find scientists who are doing that. Let us gather them and support them and see what kind of products they end up building. And then you take that and you pour it into society. So I think it's a different, like a entire different fork that we need to have the courage to take, because if the problem was caused in that fashion, I don't know how we'll be able to do it to the level it's needed from the bottom up approach. It will
Um,
jerk a few things at the lower ends for sure. It's absolutely needed. It might even be needed for an awakening. But whether it'll actually resolve it, not as long as people immediately think that light is electromagnetism, then they will not factor in many things that might even affect human health. So just the knowledge being lacking in that respect will be the result, will cause the results of bad things down the line, no matter how much goodwill you have from the consumer. So that's what I think about that.
Yeah, old ideas are such formidable monsters to face down too.
Yeah.
I came from this lab where we were building these green energy devices, really these power harvesters that worked on evaporation. They just harvested evaporation gradients, and they're super efficient. They work at least as well, watts per meter, as solar and wind, things like this. And we thought, oh, the world's going to be so excited, My advisor at the time went with this postdoc on this big tour out to the West Coast to visit with these different municipalities about maybe working with some power companies to implement some. They liked their coal. You know,
Yeah.
they were comfortable with the jobs that were coming in from the coal industry. They didn't want to have their reservoirs covered, right? They liked their boating and their fishing. Basically, they liked things the way they were, and that seems to be a huge part of what makes it so difficult to and for really sincere, brilliant scientists to bring ideas into the world. Is
Yeah.
that people are pretty happy with what they've gotten used to,
Yeah.
and I don't know a way around that per se. But it did strike me for the first time as a formidable foe in the march towards something more harmonious in the name of progress.
Yeah. 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 I mean, it's something that requires a much bigger incubation cycle than most of the startups and things like that, because you're incubating a worldview, and then through that you're incubating a different science, and through that you can incubate, and then finally downstream you have effects. And like you said, if you try to push something downstream, some things will move, some things will not move, and you get a great example of what doesn't move, because you have to deal with the adaptation, and you have to deal with all the problems that occur when only a few things are going this way and everything else is going that way. And so until an entire stream can go this way, you don't have the capacity to make the change. So yeah, one of the things I've been doing, you know, all through undergraduate and graduate school, and even after that, is trying to find scientists who, number one, spot these gaps. Number two, have an ethical core that doesn't, compromise for all the convenience and profit and glory and all those reasons, and to the best of their ability, of course, and are willing to go into it for the long haul, even if it doesn't necessarily bear results in terms of a good career and a good job and all of these things, like people who are genuinely about the science as such. They may have a degree, they may not have a degree, it doesn't matter. So that is part of the optimistic side of this, that there are indeed several such people. They just not part of the institution, not part of the mainstream, but very much capable of asking the hard questions and following them up. And so, yeah, getting those folks to work and collaborate and actually engage in something that will create this different stream, that's a big portion of what I want to be able to help catalyze. And so see how the results go, but it should be something that is very much possible.
This might be a good point to plug the conference that you're organizing.
Yeah, that is precisely what the purpose is. A conference, we're calling it Renewal of Science, and it is going to be in the end of October, so October 31st, 1st, and 2nd, 3-day conference in the Bay Area, and right in Mountain View, in the big, huge, beautiful museum called Computer History Museum, and in the top floor. And we are inviting several researchers of the kind that I've been describing, and they're all going to be coming and covering different aspects of science, whether it is color, which will be covered, or electromagnetism, or climate, or biology as well, which is a very, very, very critical subject in terms of evolution and the ideas of evolution. And there are like several of them who have created exhibits, so those who attend can actually see the different physics in action and not merely think about it or whatever. So yeah, so that's the overall uh, theme of the conference, and we're hoping that those in the Bay Area or even from afar can come and take a look at what's being produced and how the different subjects support each other. Because one of the big issues we find everywhere is hyper specialization, and if you say just physics, they're like, what do you mean physics? It's so huge. What are you talking about? Tell me which sub branch you're talking about. No, we're trying to bring in different branches and see how what one branch has to say supports what another branch has to say. And you actually see the collaboration between the different fields and the people who are doing that. So if you do want to try doing a different kind of science, well, here are the people who are trying to do. I'm not saying they're all the people, but these are the type of people that you need to be speaking to and working with, and help create a different stream with us. So yeah, that's the goal of it. A long time in the making, and COVID put its own stamp on blocking it for a while, but finally we've gotten around to doing that again. So
That's fantastic. I'm really looking forward to that. Are tickets already on sale?
now registrations are available right now, like pre-registrations. Tickets will be the sales will kick in probably in about 10 days. So I would recommend that people go online and look at renewalofscience.org. And if you just go over there, and you will link up to the website, and it'll give you the details of the topics, the speakers, the registration, and so on. And yeah, once in 10 days, we'll announce the ticketing process and everything. So
Is it are you sure that it's just renewalofscience.org? Because that's just a GoDaddy park.
well, yeah. So right now it's not pointing yet. We have the domain.
Got it.
It's renewalofculture.org is the main website,
Got it.
and in that we have the you can pull that up, renewalofculture.org, which is then going into the science tab, and when you go there,
Got it.
then you will see some of the people coming in and all that stuff. And
Very cool.
so
Yeah,
yeah,
I mean, this is such an important movement. We're kind of trying to do the same thing, right? Getting people together and starting to think about where science can go in a way that's not limited by academic narratives, and
right.
going back to the heart of experiment.
And I think you nailed two of the most important things that we need to recognize and support more than ever, which is authenticity, right? That real desire to do the work,
Yeah.
to really understand nature, and the collaboration between people who are studying things from different angles. It's like the same thing. We do a lot of music too, and it's the exact same thing. It's like, what do you need? You need authenticity, and you need people working together to make with very different people coming together. That's where you get the most brilliant art, honestly, because music's a very collaborative effort as well, at least bands, the kind of music we're into. But I think the same thing needs to happen here, and I really appreciate what you're doing with it.
Yeah. No, thank you for that. Yeah, it's I'd invite you guys to also work with us on this project and collaborate as well. And we'd love
Yeah,
to.
let us know what we can do.
Yeah, yeah. I'm sure. I mean, there are a bunch of people that you have already interviewed and explored ideas with, and I'm pretty sure some of them will be very much interested in joining hands and doing things together with all of this. Uh, and a lot of them seem to have seen the same thing with the restrictions of academia, which is very encouraging. So, yeah.
Yeah. I just had a thought. I know that you are also interested in reciprocal systems theory.
Yeah.
And this is something that we didn't get to in this conversation, but maybe it's something that we can come back to. We have several of Dewey Larson's books in the house.
You do?
And we have a patron
Thanks,
who's
Steve.
thank you, Steve. Steve is getting progressively more and more frustrated with us because we have not given due diligence to Dewey Larson's ideas, and so perhaps that could be a topic of a future conversation.
Yeah, no, anytime. That's a very huge, exploration that is super important for the world to know about. It's also a different way of doing physics. He's more of a person who comes to it completely from the domain of ideas. But he also had a long-standing experience with working at a chemical company, an oil and gas company. So you have all this experience, but what we read in his books are all his ideas. So you don't necessarily realize how the two relate. And Yeah, I'm in Salt Lake City right now because the Reciprocal System work was headquartered over here.
Mm.
So that's how, yeah, that's my connection to the topic. But yeah, we can definitely do a deep dive into Dewey Larson anytime you guys want, and see how those ideas fit in with the modern world and what is there left to discover in that pattern and the whole thing. Yeah.
Excellent. Thank you for coming by and sharing all of your ideas with us. It always, I said this before, but it always feels really reassuring to find somebody in the world who's hoeing the same row as us, so to speak.
Yeah, very much so. Likewise from my end as well. Thank you. Thank you guys so much for the invitation.